One more.
Okay, so this is the top of the left-hand column on number 5.
Yeah, I'm just trying to make sense of like if we were plugging in on this side,
What's true if that's true?
then if I could see it on both sides.
Remember the limit test?
Yeah.
If that's true, then the limit of the ratio of those two things
So, yeah,
should be a positive constant,
The
right?
pattern makes sense.
So let's take the
Oh,
limit.
is always incrementing, right?
N goes large, 2 to the n plus 3 to the n
Oh, yeah. Oh, yeah, because we're dividing it's like a
5 to the n. Okay, that's the same as the limit that goes to infinity of 2 to the n over 5 to the n plus 3 to the n, 5 to the n, and that's the same as the limit n goes to infinity of 2 to the n over 5 to the n plus the limit as n goes to infinity of 3 to the n over 5 to the n, and that's equal to the limit n goes to infinity of 2 over 5 to the n plus the limit as n goes to infinity of 3 over 5 to the n. Anything less than 1 in absolute value, the limit as n goes to infinity is 0. So this is 0 plus 0 and 0, and that means that these are not the same big theta class. If they're the same big theta class, the limit will yield a non-zero constant.
I don't remember, I was gonna go over it tonight, the process I used to figure out the omega match on that, but we never went over it this way.
Yeah, we
How
did.
would you-
I did 4 examples.
He did do that, yeah.
No, no,
Look
not
at
in
the-
class, that's all I
Yeah,
know.
in class. Look at the
But then,
bottom.
how would you be able to
Look
tell
at the
us?
bottom half of the first handout on asymptotics. It gives the top half of the test, and then the bottom half is the corresponding limit condition.
So, would you say maybe the best way to think about this is rather than look at both sides, try to maybe just isolate the
Yeah, so the
specific
exponents can only add to the
complexity, kind of like what you did here? It's like do 2n plus 3n over 5, and then you said that you can like
I
substitute
think
values
that, I
that way.
think that since these are statements about, these are positive assertions about asymptotic relationships, that you're going in the correct direction in the conditionals in the handout, so that you want to do the limit first. So I would start out in each one of these cases, I'd start out by taking the limit of one over the other as n grows large, and decide what the convergence behavior of that limit is. And if it says they're big theta related, the results of that limit process should be non-zero positive constant. If it's divergent, that means that the big one is either big O or big theta, big O or little o of the lower one. And I mean, the key problem is deciding which of those two it is, right? If you have something that's little o, means it's big O but not big theta. Okay? And same ways, little omicron means it's big omega but not big theta. So those are like less than and greater than, as opposed to less than and equal to greater than. And since these are positive assertions, then you should do the limit process first. And the limit process says, if the limit turns out like this, then you're guaranteed that wasn't the relationship. The left-hand side was a big O, big theta, big omega relationship, and the right-hand side was the limit result. Okay, so do that first because that's the cheapest. Okay, and for all of these, that's going to work. Okay, you want to just walk through them one at a time?
Sure.
Everyone set?
Yeah, let's do it.
Before you did that, could you clarify how the last two limits evaluated out to 0?
Yeah, anything that's less than 1 in absolute value, the limit is 0 as its exponent goes to infinity.
Okay, perfect, thank you.
Let's see. Where did that 0 go? Did 1 go left?
Yeah, she said she
I
was.
thought she wanted to see this. Do you have all this data? Can I erase this now?
Yeah.
Okay. Okay, next one, n squared is big O, 2 to the n, and what does that, I mean, what does that mean? It means that big O, as n grows large, 2 to the n is bigger than n squared. So the limit test is true if the limit as n goes to infinity of n squared over 2 to the n equals 0. Okay. Now just apply L'Hopital's rule twice. And you have a positive function of n in the denominator and a constant in the numerator. Constant over an increasing function of n equals to 0. Okay? Questions about that one? Okay, how about the next one? N okay. This says intuitively the function f of n equals n is bounded below by the function f of n equals 1. My intuition says that's true, and what would you do in terms of evaluating a limit here? Well, if this is true, then that implies that the limit n goes to infinity of 1 over n equals 0. Is that true? Yeah. And so, I mean, it's basically the same thing. Let's take a look at the next one. It's a little bit trickier. Okay, so what this says is that n is less than n squared over 2, and not less than or equal, and not equal. Okay, so if I put this over this, this is the function, and this is the lower bound. I would expect n squared over 2 in the limit, as n grows large, I would expect that behavior. Okay? If I take that limit and they're the same, then they're in the same big theta class. And if two things are in the same big theta class, that's another good thing to remember. If f is big theta of g, then f is related to g in that way, and f is related to g in that way. Okay? Because these are both less than or equal, greater than or equal.
Thank you.
Do that. Okay, so that one, the answer is true. Let's see here. 2n squared, little o, 3 plus n squared. Okay, that one is going to be false, and the reason it's false is because to be little o, you can't be big theta. To be little omicron, you can't be big theta. Those are strict, okay? So it's not less than or equal, it's less than. It's not greater than or equal, it's greater than. And these two are going to be in the same big theta class. So f of n equals big theta of g of n implies it's not the case, f of n equals little o of g of n, and it's not the case that f of n is micron. Because this says they're the same. They're the same because if I take the limit of the ratio, I get a positive constant. Okay? So they're the same big theta class. If they're the same big theta class, then it's not true that one's strictly less than the other or strictly greater than the other. And that's what these two symbols mean. Okay? Okay. Let's do the next one. Can I erase this? Okay. Okay, so what does little o mean?
It's bigger than but not equal to the limit of infinity.
So what this is saying is that n squared is greater than 2n. I'm going to put little quote marks to remind you that that's not really what that means, but that's true, but they're not the same. How about this one? How about if I put 2n squared equals little o 4n squared? True or false?
That's similar to the third one on the right.
So it's false. The reason it's false is because these are the same big theta class. If you take the limit, then you get a positive constant, in this case 2, okay? You get a positive constant, that means that this is big theta of this. And if two things are big theta, they're automatically big O and big, whatever the other one is, and they're automatically not little o and little o micron.
And I forget, is that the same with addition and subtraction too? Like the third one on the right, where it's n and.
There what I would do is when I would take the limit, I would put the sum or the subtraction on the top and then break it up into two fractions and do the limits independently. The way we do is 2 to the n over 5 to the n plus 3 to the n over 5 to the n. Yeah, and if they're both sums, then you have to use L'Hopital's rule. That's the big advantage of L'Hopital's rule, is that they can be like anything, as long as you can differentiate them. You're okay. Kareem, you got one while they think up their next one?
Oh yeah. I didn't